afternoon, everyone. My name is Karen Kanapstein. I'm an editor with Shield Wall Media. I thank you for coming to the Rollforming Show, and on behalf of Rollforming Magazine, welcome. I'm here to introduce Brad Shreve with AkzoNobel, who is going to introduce you to, I was going to say coil coating. Is it strictly coil or is it?
Introduction to coatings.
Introduction to coatings.
Thank you very much. Hello, everyone. It's a pleasure to be here. First, I'd like to start out by saying you are definitely the smartest people at this show because you're here. Regardless of what business you're in, I think you need to care about the coatings. Before I go any further, I would like to make a special thank you to Shield Wall for hosting this. Special thank you to Diane Sims for all of the setup, for everything we do here and getting this coordinated. And very special thank you to Brian Thomas, who's collaborated with me on this presentation. And by collaboration, I mean putting up with my shenanigans. So to get right into this, this is what we're going to talk about here for the next hour, 45 minutes. Talk a little bit about AkzoNobel. Who are we? It's interesting sometimes how we're not as well known as the other companies. But this is Coatings 101, an introduction to coatings. So we're going to go real high level, talk about what coatings are, regardless of coil coatings or any other application. Really, at the end of the day, there are main ingredients that just about any type of coating is comprised of, and then the details are down the line with the specific formulating per application. So we'll go into a good bit about paint and how it's made. Then we will sort of funnel down a little more into coil coating specific. That's really why we're here. The coil coating system, a little bit about how we test and get paint out the door. Real world testing. This is a very important part of this product, but really anything that goes into service is how is it going to perform in the real world. And then lastly, we'll certainly take questions. A little bit about me real quick. I'm quickly approaching my 25 years in the chemical industry. I started out in rubbers. My specialty is polymers, so plastics and rubbers and all that stuff. And then sort of accidentally transitioned into coatings sort of in the early 2000s. Still worked on the polymer side, but I began R&D for polymers for coatings, and then that got me into coatings. And I really haven't looked back. Coatings are really fascinating. I would challenge anyone to find something in this room that is not coated. Seriously, I mean, coatings are ubiquitous everywhere around us. They serve every function you could imagine. So real quickly, AkzoNobel. We're going on 230 years of business. That's pretty astounding. If you caught Doug Irby's talk earlier today, Akzo was comprised of many different segments, from specialty chemicals and pharmaceuticals and coatings and who knows what else. But the common theme all along these 230 years really is coatings, and coatings is at the heart of what AkzoNobel does. So a few years ago, we did spin off and divested some businesses, and now we are strictly a coatings company. We're very focused in coatings and a full array of coatings. Globally, we cover every coatings market that really there is: decorative paints, marine, automotive, industrial, powder, and so on and so forth. We are in the industrial coatings segment, so that includes coil and extrusion metal coatings, packaging coatings for food and beverage cans and things like that. And then wood coatings falls into that line, so anything that coats wood. You'll notice a few, if I get this pointer to work, Trinar here, Ceramistar 1050. This is really why we are here today. We got Polymer there too. These are our trade names, our brand names for coatings that we specifically manufacture for metal coatings and coil specifically. AkzoNobel does have a huge line of decorative house paints, but in the United States we don't operate in that market. I think that's generally why people but across the globe we do. So this is our facility in Columbus, Ohio. Right up here we got, you know, the normal offices and lab, and then it goes on to the main manufacturing facility. It's quite large, and in my opinion, it's very impressive. It's the cleanest manufacturing facility I've ever seen, regardless of industry, rubber, coatings, anything else. We take a lot of pride in our quality and our cleanliness. So all of the products, for the most part, come out of Columbus, Ohio. We have R&D labs here, other functions, and then certainly we have a supply chain with resins and other things throughout the Midwest. So here we are, paint, how it's made. Like I said, we're gonna go high level, work our way down a little bit. So this is just paint and coatings. You know, a very broad class. So paint, I like this definition. I like that it's very simple. It's just colored, you know, they say colored, it doesn't have to be colored, but it's a liquid you spread over something and it serves a purpose. Of course, it's a verb too, paint, you paint something, but we're talking about the noun. And decorative, protective, and functional. These are the main categories that any paint and coating would achieve. And it's interesting, in Coil, we actually hit all three of these. Coil coatings are certainly decorative. We have beautiful paints, make beautiful roofs and other buildings. Protective, for sure, we're protecting the metal substrate and the structures that are comprised of that. And they are functional. You know, our coatings shed dirt and water, reflect IR, infrared light to keep a building cooler, and so on and so forth. So again, high level, 4 primary ingredients in a liquid paint, okay? We have pigments and fillers, and this really this group is all of the dry stuff that would go into a liquid paint. These are powders and other forms. They go into the paint at the beginning and they stay there the whole time. They provide the color, opacity, hiding, you know, a red wall is hiding something behind it. Pigments and fillers offer a lot of the durability properties, and even specialty with corrosion protection. Resins, so these are the polymers. This is the sticky stuff. We oftentimes talk about binders. This is the liquid portion that goes into a coating and really binds everything together, keeps it in one place. It's what allows the coating to stick to something that it's applied to. Certainly it offers the flexibility. Maybe it's very flexible, maybe it's not so flexible and cracks. This would be a property of the resin. Solvents and additives, I mentioned them here, they're extremely important to any coating formulation. I'll talk a little bit more about them, but for our purposes, not much more. Huge class of chemicals, but at the end of the day, we're coil guys, we're roll formers, we really care about the final product. And solvents are gone. Solvents do not remain in the final product. Additives do, but as the name implies, they're an additive. Very small amounts are used, sometimes under 1%. So although they offer a lot of the properties to the coating, for purposes of today, we could never go that specific. It's really important from my perspective, if I'm gonna talk about a topic like this, and you have to understand 2 broad classes of compounds, chemical compounds. Okay, the broad classes are organic and inorganic. And there's a lot to it. I mean, this is what makes up the chemical industry. We spend careers, you know, centuries studying this stuff, but in the broad category, we have organic compounds, and really they're just compounds that are made up of a lot of carbon, a lot of hydrogen, oxygen, nitrogen, and very little else. And there's just an infinite array of combinations that these atoms can go to make an organic compound. And they really offer some interesting special properties. Our resins, polymers for example, are an organic compound, even though they're not organic in the terms of an organic tomato, or they were not derived from any biological source for the most part. That is an organic compound. I have caffeine here, so I have them divided up. So caffeine's an organic compound. It's an interesting compound. We all know caffeine. To be frank, my presentation right now is fueled on caffeine. You know, we know it, but it's an organic compound. It's relatively flat, very little structure to it. By and large, they're insoluble in water, low melting points, poor conductors of heat and electricity. And a couple examples here. We have gasoline, milk jugs, tire rubber, our DNA. Those are sorts of organic compounds. And then we have the class of inorganic compounds, an enormous class of compounds. They're generally geologically based, mined from the earth, clay, sand, you name it. And they have extremely different properties than an organic compound. So here I'm showing calcium fluoride. I think it's a bit of an interesting one. What you're seeing there is the red and the green come together and they make the molecule. But what's interesting about an inorganic compound is its tendency to want to stay together, right? It wants to kind of be amongst its friends, and so they pack together tightly, which is why we have this cubic structure to show how they pack together. You don't have individual inorganic compounds. So that makes them clumpy. Think of a clay, you know, something like that, where it kind of wants to stick together. But on the flip side, from an organic compound, they're characterized by very high melting points. They're generally good conductors of heat and electricity. They crystallize easily. Think of table salt. You know, you pour out your table salt. Those granules are millions of these atoms bound together to make a crystal. And to kind of further compare and contrast the two, calcium fluoride, its melting point is about 2,500 degrees Fahrenheit. And caffeine, ironically enough, its melting point is right in the sweet spot of a coil coating oven, 460 degrees Fahrenheit. So you could actually throw some caffeine on a coil and melt it as you make your paint. So to go on with the ingredients to go into a paint, we want to start with the pigments. Again, like I said, these are the dry things, pigments and fillers. They go in dry, they stay dry, they're there for the long haul. And they really come down to three main classes. We have inorganic and organic, which is why I had the previous slide to discuss those. And then we have ceramic, which is a specialty type of pigment. It's inorganic, but it's a different type. So if we go down the list, organic, like I just mentioned, low melting points. So again, heat can begin to degrade these things and change their properties. They are engineered. There is not an organic pigment that's naturally extracted from the earth and used. They're engineered from hydrocarbons, basically crude oil that goes through the whole chemical supply chain, and just an endless variety of things are produced, and organic pigments are one of them. We have inorganic pigments, like I said, mined from the earth's crust. They're generally metal oxides, so you have a metal and then a non-metal, and they bond together and make something like iron oxide, which is rust. There's different types of rust that were actually used, believe it or not, as pigments. We put rust into paint all the time. And then we have ceramic pigments. We bring this up because we utilize ceramic pigments. They are inorganic, but they're highly engineered. They're not natural at all. They're used from inorganic ingredients that are mined from the earth and then highly engineered and processed to make this really resilient pigment. Some of the advantages of a ceramic would be a nice selection of colors. They're extremely durable, resistant to heat, chemical attack, moisture, and very light fast. Inorganic pigments, we really like inorganic pigments. They almost do it for us. Very light fast, which means they don't fade a lot over time with exposure to light. They're quite opaque, so again, it hides well. You know, we can use a paint with inorganic pigments and really hide the things that we like to hide when we paint. But they don't have the greatest range of colors. Inorganic pigments tend to be earthy tones. Imagine that. They come from the earth, earthy tones, browns, pastel-y things, and these days we want a lot of vibrancy in our colors. We want a wide variety of colors. You look at the fan decks we have these days. So it gets us to the organic pigments, which even though they're much less stable, that really can provide a lot of the vibrant colors we need to achieve the color spaces we need. So we use them in very small amounts to get to the colors we need, and we try to either not use them at all or use them in small amounts. The ceramic pigments have replaced a lot of the use of inorganic pigments, and we like that because they're highly durable. Next would be the resin class. So again, these are polymers. This is the binder, the sticky stuff that really holds the paint together, makes the paint film. It is the backbone of the coating. Without the resin, you would just have dry powder that would blow away. So you know, we use a variety of chemistries to make these. What I highlighted here are really the main class of coating chemistries: polyesters, silicone modified polyesters, our Ceramstar 1050, acrylics, epoxies, polyurethanes, polyvinylidene fluoride, that's our Trinar, phenolics, and the list goes on, but these are the major classes that would comprise a resin or resins that we blend together to make a paint. Some coating manufacturers source, so there are many, many companies that make resins just to sell to coating companies and others. And then other companies actually manufacture their own resins. AkzoNobel is one of those. We do manufacture our own resins, and we like that for many, many reasons, but really control would be the #1 key. We can control our quality, and we can dial into the properties exactly as we want them. And then, you know, really the resin imparts all of these qualities that we want in our finished roof or other product. Gloss retention, we don't want it to chalk. You know, we want it to stay where we put it, so we want it to stick and not hold stains and dirt. All of that comes from the resin. As I mentioned, I'll touch on solvents and additives one more time. Here it is. So solvents. Think of, well, gasoline, water, all these fluids can be solvents. We use our coatings for coil or solvent-based, kind of the stinky stuff. So we do use hydrocarbon-based solvents. It disperses the resins and pigments, helps us actually process the paint in manufacturing. It's critical to the application of the paint, how the paint is applied on something. Solvents are extremely critical, but again, they don't remain in the final film, so this is the last time I'll talk about them. And then we have additives. Myriad variety of additives. There's an additive for everything, I kid you not. Some of the biggest companies are additive companies because the selection is endless because it needs to be endless. They impart just about any property you could imagine. If you take a paint, gallon of paint, divide it in half, you got 2 half gallons. Gallon A, you add a bunch of additives. Gallon B, you add a bunch of different additives. You're going to have an extremely different paint. Even though they're in at very low levels, you're going to have an extremely different product. And then I just have a little cartoon here just to show, you know, a type of additive. This is actually a surface additive that would help inhibit rust, right? It's repelling water. It's a way, one of the many ways to inhibit rust formation. So we talked about the main ingredients. I like this because it's a way to somewhat visualize what I just threw at you. I'm not going to go through a formulation and get specific into what's what, but I like on the left, it's a nice way to sort of visualize the breakdown of, this is a 55-gallon drum, which represents it's full of paint, and I like how they have this dotted line here. It's basically 50-50 solid stuff, it's not going anywhere, and then the liquid stuff. Some of the liquid stuff stays, most of the liquid stuff leaves, so you're left with the solid stuff. So I like that graphic. On the right, I actually borrowed this from Doug's presentation earlier. I made a little modification just to show the vast range that these different ingredients can go into a coating. It really depends on the coating that's needed, the coating type. A clear coating. You know, we would think a clear coating wouldn't have any pigments in them. They actually do. Most clear coatings do have some dry, transparent. They're not, you know, they make them clear, but they are in there. So you know, anywhere from 10 to 60% of a coating would be the dry stuff. But that just shows a nice range of the variety that we can come up with. So here we are. We have our ingredients. We know how to use them. We want to put them together now on an industrial scale. We really have to know what we're doing to do that. We can't dump everything together and stir it up with a spoon and be off to the races. It doesn't work that way. we're dealing with a highly complex system. Coatings are classified as a highly complex system. We're talking about hundreds of different molecules in one pot that have to come together. We have to keep them together. And oh, by the way, they don't want to be together. That's where the skill comes in. They do not want to come together easily. So if you think about manufacturing an automobile or something else, there's these sub-assembly sections, right? You make some car part, put it aside, make another car part, put it aside. When you're ready to make a car, you put it all together. That's really the same thing we're doing with our intermediates. So again, we're talking industrial scale. We would make our paint intermediates, and that includes the resins, some fillers, all the ingredients we talked about. We basically do put it to a big vessel, mix it up. It's not too difficult. Of course, there's the chemistry side. You need to know what you're putting together, but getting it together is not too difficult. We have ways to make them stable for further use. And then separately, we make our pigment concentrates. So this is really where the skill comes in. Like I said before, pigments are generally inorganic. We have a small class of organics, but inorganics, they want to stay together. They don't want to be broken apart and dispersed. They like being with their friends and their family. Of course, we have to get these dispersed very finely to have a nice smooth coating that would serve all the purposes we need. So again, like the paint intermediates, we have pigment concentrates that include mainly pigments, some resins, some solvents and additives. But the important point here is the medium to high energy versus the low to medium energy for the paint intermediates. This is where the skill, the time, the effort really goes into paint manufacturing to get these particles finely dispersed. So we're going to talk about this for a minute, because this is really, you've got to know what you're doing. There are special techniques to do this, and if you don't properly disperse your pigments, you will have problems. One example I like to use is you don't have pigments dispersed properly. Now we're talking coil coating line. We go ahead and apply this paint with improperly dispersed pigments. It goes through a very high shear process when the coating is applied. That high shear process is going to further break down the pigments, and it's going to change your color. You're going to have a different color on the other side of the line. So here we go. We have milling. This is very high energy, time consuming, relatively small volumes, and it's ex situ. So it cannot be done in the same vessel that you're making the coating, the final coating. It has to be done in a completely separate process. That was great. There are companies that actually make nothing but pigment concentrates. They have all the highly specialized equipment to do it. You can buy dispersed pigments from these companies. Next would be the high-speed dispersion. This can be in situ. It means it's all done in the same vessel. We just keep adding our ingredients in an appropriate order. It still uses high energy, not nearly as high energy as milling. It's somewhat less time demanding because of the fact that we're adding it to this vessel and we can continue to break these particles down. And then there's a class of pigments, they're stirring pigments. So they're engineered and they're purchased intentionally to be stirred in. You add them to the pot and they're easily dispersed. Just by mixing and stirring, we already have the particles dispersed and stabilized. So the grinding process, and this is really, you could have paint company A, paint company B, give them the exact same ingredients, exact same formulation, but not tell them how to put it together. Just say, here you go, make a paint. They will make very different paints. It depends on the skill, the know-how to grind and disperse these pigments, and then differences in equipment and all these things. So what we want to do is grind these agglomerates. So they're agglomerated together. These are these clumps that don't want to come apart. Now we have to get them apart into their primary particles. That might be down to the molecular level or just very, very tiny. And then we need to stabilize them so they stay that way. We do not want them to come back together. They want to come back together. So even if you disperse them and as finely as possible, if you do not stabilize them, they will flocculate. Little small clumps here, they flocculate, and they will eventually, as they're sitting in that can, come back together, and you got problems. So to visualize what I'm talking about here, we have the two main grinding processes. We have high-speed dispersion. So what we're looking at here is a vessel. This is a container full of red paint. And we have a mixer shaft coming right down the center, and spinning on that shaft are blades that look like this. And there's many, many different types of blades. You can see all sorts of geometries with teeth and no teeth. And really, they're designed to move a certain type of liquid, whether it's a thin liquid, a thick liquid, there's a variety for that. But what's happening as this mixture is going on, you can see the lines of flow. Lots of people think that these teeth are actually sort of cutting these pigments apart. That's not happening at all. You're talking about the tooth of a blade is thousands of times bigger than these small particles. They're not cutting at all. The blades create a special type of flow at a very, very high speed that is causing these particles to collide. And they're just slamming into each other and slamming into each other. Over time, it builds up heat. Over time, these particles tend, as they slam together, they start to fall apart to their primary particles, and we stabilize it that way in that process. And then there's the milling. This is the one that really, really is specialized, takes a lot of time and energy. As I said, it's ex situ, so it's a completely different process. You're not doing it in the same tank that you're making your paint. And so what it is it's a process that puts the paint in one end and it comes out the other end, okay? But what's going on in there is we have these teeth, these sort of long arms, if you will, and they spin around on this shaft. They're spinning and spinning. But what they're spinning in is this grind media. All these dots represent these guys right down here. And just like blades and everything else, you can imagine there's an enormous variety of grinding media. Think of sand. That's a media that's used a lot. So this vessel is filled with this media. Paint is pumped through. These teeth are now mixing through these beads or sand, and it's causing a tremendous amount of shear and force grinding and grinding these pigments apart. No different than millennia ago when the grinding wheels to grind pigments the old way or grains, the grinding, it's just this attrition over and over, and eventually they come apart, they're stabilized, this is packaged up and sent back for further use. And I should add that the media is extremely dense and hard. They're generally ceramics, very, very heavy, very, very hard, and they can just pound away. So now we're ready for assembly. We've made our parts, we have everything ready to go. We're a large paint company, we have a very large menu of products that we can offer. We would never ever be able to manufacture from start to finish every product from scratch. There's no facility big enough and people, and so we have these intermediates now that we've specifically formulated so we can put them together in the different proportions and add our special additives and shoot out a product that is appropriate for your needs. So we're putting the intermediates together here. So I have this graphic where we have our paint intermediates, our pigment concentrates, the additives, and really we just squirt them out, we blend them together, squirt them out, and then we have our final product. No different than if you go to a hardware store, you have your gallon of paint, you want it colored. Although that paint's a finished paint, they squirt in their color, mix it up, and you have your thing. That dosing unit is exactly the same thing that we use, just we're bringing the final product together. We're not only adding color, we're adding other ingredients that have been pre-made to the paint. So these are nice photos. These are photos of our automatic dosing unit, an Intermex sort of blending system. And blending can be simply adding ingredients to a pot and blending them up. And there's different ways to add them to the pot. And so this is our automatic dosing unit, and what you see are just tanks after tanks. This is by no means the full image. There are different images, but these are tanks full of intermediates that we make. So our main manufacturing process really goes into the intermediate part. That's where the time and energy goes. So when it's time to fill an order, we have these ready. We can mix them together, and out the other side is our final product. This is the action part of our automatic dosing unit. It's a little difficult to see what you're looking at first, but what you're seeing is a very precise, highly engineered piece of equipment that literally, this red here is some colorant, some red intermediate that's being shot into this hole, and underneath the hole is a 55-gallon drum. So each one of these little cylinders is a different dosing head. Okay, it's attached to a different vessel, which is attached to a different intermediate. So we have a computerized system. We can call up a recipe, and just one after another, the drums go through. That specific formula is dosed into this vessel. It's mixed up, and it's sent to quality control. Here is an image going in. So this would be where the dosing heads are that you just saw. And this is where a drum or any other sort of container would roll through. It would be dosed, and off it goes for packaging, QC, and filling. So it's extremely efficient, it's extremely fast. Now we're able to make a variety of products in one day because we have all of these ingredients ready to go. So coil coatings, we'll get a little more specific now. Certainly we're the coatings guys, we're not the actual coil line guys, but we have to talk about it a little bit. It's a phenomenal process. My time at AkzoNobel is my first go around with coil coatings. All my other coatings experience was other than coil, and generally spray applied, brush applied, the normal coatings applications that we're used to. Coil coating is really complex and really, really impressive. We're talking about speeds of 300 to 700 feet per minute that this web of metal is rolling through this industrial process. As that's happening, coatings are being applied to both sides. We have multiple layers of coatings being applied to both sides, and out the other side comes a beautiful, very smooth, pristine, organic coated coil. And here it is. This is kind of a nifty little thing. It shows the process overall. I'm sure a lot of you are familiar with this, but what's so impressive and what really makes a coil coating system be able to be a coil coating system are these towers. We have entry towers and exit towers. And I don't know, we have other experts that know more than me, but I mean, there's several stories high. These are very, very tall towers. Each one of these rolls, so it's they move up and down, up and down. So you can imagine as this coil's rolling through, as the tower goes up, it's collecting more metal, right? It has more metal than it did when it was this tall. Now it's this tall, it has a lot more metal on it. So that allows further down the line for things to be done. As there's an accumulation going, they can stop a part of the line, do their things, and be off to the races again without stopping the entire line. And that's really the thing. That's the beauty of the efficiency of the coil coating process. You can see that cleaning happens. The paint's applied. It's cured through one oven. It's applied again. It's cured through another oven. And at the end, it's coiled up into a very nice, beautiful coil. So more of what we want to talk about is the system. The paint system certainly, but when we talk about a coil coating system, we have to acknowledge the entire system. So again, if you're into roll forming or whatever part of the business you're in, you're dealing with the whole system. You might be a steel guy, you might be a metal guy and really like that, but you're also dealing with paint. So that's where we're at now. And again, at the end of the day, it's ready for the roll formers. It's off the line, it's ready for the roll formers to do what they do. So we're going to transition from the liquid part of putting it together to the dry part. And really we need to look at what ends up on the roof or wherever else. What is a paint film? So as I said, the solvents go away, we're left with all the dry stuff. We have to think about the film at the small scale, and really it comes to this is critical. There's particle packing theories, okay? And the way I like to use the analogy, if you take an empty swimming pool and you fill the empty swimming pool with basketballs, okay? These basketballs are gonna nestle in together. You're gonna have really big open spaces still, right? Imagine all these basketballs, you got open spaces. So now you wanna throw in some baseballs and get it mixed up. And those baseballs will fill some voids. And then add some ping pong balls. And you see where I'm going, to the point you're adding sand, okay? And all of these voids are being filled up by solid particles that are going nowhere. And you can see how they pack, right? We have our voids here, and I like this because it shows the progression. We're filling voids, and you know, down to the fact that, you know, very small spaces, and what fills the rest of the space is the resin, right? The polymer, the liquid part that binds all of this together. It's cured, it's hardened, and then you have what we have on the right. So we're down very small. We're looking at like a 50 micrometer, 50 micron level. This is the cross section of a coating. So if you take a paint film and just slice it, we're looking at that sliced end here with a microscope. And clearly it's some sort of blue coating. We can see blue dots. That would be a blue pigment. We have, you know, other white and beige things in here, but what you see is this packing, right? We have different size particles that were intentionally put into this paint in a way that we want them to pack to a certain density. Some coatings are not packed very well at all. Other coatings are tremendously packed full of tightly packed full of dry things. So this is what we're looking at. This is what we want to achieve at the end of the day. As I said, all those voids and everything's bound by the polymers, by the resins. Two main classes of polymers. We have our thermosets, which is what coil coatings are, all thermosets. Thermo meaning heat. And then we have thermoplastics, okay? So thermosets, a chemical reaction is happening. We have a liquid resin, we apply heat, and out the other side comes a dry paint film. However, the chemical reaction that happened inside that paint film is cross-linking. So if you imagine a plate of spaghetti noodles, you can pull out a single noodle all day long. Pull them out. No interference at all. You can pull that noodle out. These polymer resin molecules are just like spaghetti noodles. They're intertwined and sliding across each other. But what we've done is we've initiated a chemical reaction to now create these cross-links that chemically bond each noodle to the other. So now if you want to pull out a noodle, you're going to pull out a whole clump of noodles because they're actually bound together. This is what makes coil coatings so extremely durable and resilient, as opposed to thermoplastics. So thermoplastics are types of polymers and resins where you can make a dry film. A wall paint is basically a thermoplastic. There are some reactions these days we're so advanced that coatings can happen, chemical reactions at room temperature, but by and large, it's a thermoplastic. And what a thermoplastic is if you add heat, it will become pliable, soften, and even become liquid again. Think of a milk jug. A milk jug is a thermoplastic, and by virtue of being thermoplastic, we recycle it. The recycling guys take it, they melt it down, and they reuse it. And they can do this infinitely many times as long as they can keep it clean. Whereas a cross-linked resin polymer, you're done. It's set by chemical bonds. There's nothing you can do to break these apart. And eventually, all you can do is just ruin it. If you were to add heat, it would just become brittle, useless. So that's the main difference there. And we are the cross-linked coil coatings. And it's important to realize that it's a very delicate process. These coatings are formulated very specifically to run on specific lines, coating lines under specific parameters for specific end uses. And really, like I said, with the caffeine melts at 460, so we're kind of in this sweet spot of the metal temperature that we want on a coil line. So anywhere about 400 up to 500 degrees, that's where our coatings are formulated to really achieve the properties we want. If you don't add enough heat, you're not going to form those crosslinks sufficiently enough, and the paint will be sort of useless, doughy. It'll fall apart. Too much heat, the other thing happens. Too much cross-linking happens. Other degradation processes happen, and the coating can be useless on that side. It can be too brittle, maybe doesn't adhere very well. That is what's going on through the coil coating process. So now if we talk about the system, I like to work bottom up We have the steel. We all know this, steel or aluminum. The next part of the system would be the metallic coating. Okay, this is not done by Akzo. This is a different part of the steel or the substrate making process. A metallic coating is generally applied. A pre-treatment, again, not an AkzoNobel product, but a coating is applied there. And then we get into our coil coatings, which would be a primer, a top coat. On the reverse side, it's the exact same thing, except that green would actually be a backer. It wouldn't be the same color. It would be an actual different chemistry of product to serve as a backer. So the substrates, two main classes. We have steel and aluminum. These are the things that are being prepared to further be coated. In our industry, we use the term substrate to include the metallic coating. So we have steel, but then we have steel coated with other things to make galvalume, HDG, you know, they're coated with zinc and other things to give it its initial properties. And then this is further coated by the pre-treatment. The pre-treatment, as I said, is not an Akzo sort of product. It's supplied separately, but it's critical to the system to start tying everything together. They are generally a dilute acidic solution. A chemical reaction is usually happening on the surface of this metal. It's inert, very crystalline, and what it does is it enhances all the properties to allow us to begin applying our liquid paints. So the first layer that we deal with would be the primer. So we have an organic primer coating. A primer by definition is a sub-layer. I suppose if you had a single coat, it would be a primer and a top coat, but you know, a primer is a sub-layer that's intended to accept a coating on top of it. It's critical to the system. Generally our top coats, you can't have the best of both worlds, so a top coat can't stick well enough to a pre-treatment and serve the other purposes that we need it to serve. So we have this primer to do that job for us. A variety of primer chemistries. We have urethanes, polyesters, epoxies. They all serve their purposes very well. The main distinguishing feature I'd like to point out is actually the UV stability. We think of a primer, it's underneath another layer, who cares? UV light can penetrate through solid objects to a certain extent. And depending on the color, that UV light can travel further or not. So it was learned a while ago that the actual UV stability of a primer matters if it's going to be exposed outdoors. So we like to use urethanes and urethane hybrids to have this UV stability, but these others serve great purposes too. Epoxies, very durable, not UV stable, but they're great for adhesion. And I wanted to point out the pigments that go into a primer, they're not pigmentless, even though they're going to be top coated and people don't really care what it looks like. Pigments are critical, and for our purposes, we want corrosion resistance and some added hiding. And then we have the top coat. This is what everyone sees. This is the beautiful part. This is the part that's, you know, sold, if you will. And it's the outermost layer, right? The top coat, no matter how many layers you have, there's up to 4 or 5 coat systems. The top coat's at the top. So it provides all of the aesthetics, the beauty, the gloss, but certainly it has to be resistant to scratching. It has to be able to be transported while it's coiled up. It has to go through these rigorous roll forming processes. Very, very complex system when it comes to coil. If you apply a house paint, you don't have to worry about a house paint being abraded in transit and all of these informing, you know, you don't have to worry about that. So this is what makes coil so complex and interesting. As I mentioned, you can have clear coatings, however, that's not too typical for the top coat of a coil. Our chemistries, polyester, SMP, PVDF, and so on and so forth. And then our backers, so the top coat of the opposite side. Now it's not really seen, so the aesthetics don't necessarily matter as much. You don't have a huge variety of colors and glossiness. We need it, and we need it to seal that system completely together. The backer is also going through the roll forming process. It's also going through transit, so there's abrasion that's happening. It has to serve certain functions. Generally, backers, polyesters, and epoxies. And it is important to note that the gloss of the backer and the top coat need to be very similar. The gloss, the shininess, and if they're not similar enough, we can get pressure modeling, and that creates a splotchy look on the surface. So it's a point to remember, a point to note. Now we have all these systems, we've made our products, but we all care about quality. We need to control our quality. I just have one slide on this. When you're making a liquid coating, there's a wide variety of tests that are done, a wide variety of tests that need to be done, but it's industry and use specific. So I have this slide. This is specific to coil coatings. And this is not an exhaustive list, but what we care about with any coating would be its density, how much solid stuff is in there, so we know what's going to be left behind after we apply. The viscosity, how thick it is, color and gloss, how resistant it is to solvents, these sorts of things. This is what matters in the coil world. So this is what, again, not an exhaustive list, but this is what we would look at in manufacturer. This is what would be done in quality control. If something doesn't meet a specific parameter, it's sent back to manufacturing, adjustments are made, and then it comes back to quality control, hopefully to achieve its final goal. And from time to time, if you have to scrap a whole batch, you have to scrap a whole batch because we need to put quality out first. Then, this is where the rubber meets the road, right? We want to install, we want to buy, we want to use this stuff. How's it going to perform? And really the only way, just like a race car test track or any car, you're not going to make a car and then not test it. You're going to drive it. You're going to drive it really hard. You're going to take it around the track until the wheels smoke and whatever else happens to a car. It's the same thing. We get our products, they go in extreme environments. We're mainly talking about roof coatings. They're seeing all the elements all day, every day, intense sunlight. We need to know how these products perform. There's accelerated ways and artificial ways to do this, but if you don't do it the natural way, which means put it into its actual service as it would be sold, you'll never really know. So why do we do it? We have our warranty issues. Doug talked about this earlier. The reason we're able to supply and provide the warranties we have is because of all this testing that has been done. Calculated risk, but we know how these products perform, so we know what sorts of warranties we can tie to it. Certainly we want to discover and mitigate failure modes. Maybe there's a new technology, something. We have to test it this way, put it through its paces to see how it performs. Compliance requirements, I deal with this all the time. A perfect example would be AMA. AMA is a body that they can certify products, and you have to prove that these products have been tested real world outdoors for a certain period of time, and they have to meet certain criteria after that time. So again, we do all of these things. And then of course, service life prediction is kind of what we're all after here. As technology changes quickly, you don't have 10 years to wait to see how a product performs, because 10 years go by, technology's already changed, and what was the point? So we gather this data so we can make really, really accurate choices based on data as to how these incremental changes in a formulation will affect final properties, so we can predict its service life. As I mentioned, natural weathering is really the way to do it. We all have artificial and accelerated, don't get me wrong. We use it, everyone uses it, it serves a purpose, but you have to expose and test in natural conditions. Just about everyone does that in Miami, Florida. Miami is the only subtropical region of the United States. So it's very humid, lots of intense ultraviolet light, temperature fluctuations. It's really just perfect to be in an extreme environment to test a product. Again, sunlight, temperature, condensation, humidity, but then your real world, there's all sorts of other things happening between dirt and acid rain, biological things, even bird droppings will ruin a paint. So we need to look at all of that stuff. And then here we go. This is a weathering, a photo of actually some of our panels on test. Not the most exciting thing to look at. It's dried paint just sitting there. But what's exciting is what you get out of it, right? There's so much data that we can get out of this to make sure we're continuously improving our products to meet the needs of all the coil demands. So what you see here is this guy with his fancy gloves, and he's unscrewing this little wing nut here that holds down this metal flap. So this top third of this panel is covered by this metal flap. The bottom 2/3 are exposed to the elements. Again, Miami, Florida, so severe exposure. And so what we have is we're able to at least block the UV. Of course, it's still going to get wet and get hot and cold and all these other things. But what we're able to do is quickly discern differences in performance, right? How light fast is this product? Maybe does it erode really easily with rain and wind? That allows us to have a very quick comparison. And then we can use this panel, take back to the lab, do further analyses and measurements. So here we are. I hope you all learned something. Not intended to make anyone a paint expert, but hopefully you can be more educated in the system that you're all dealing with one way or another. We talked about paint and how it's made of ingredients that they don't want to be together. We have to use ingenuity and chemistry to bring them together, to keep them together. We have to make intermediates to be efficient about this. We applied the coil coatings through a really sophisticated line that does a lot of things in a very short period of time. We talked about the system and how important it is to think of the whole thing as a system. You might not be a paint guy, so you might not care a whole lot about it, but you've got to care a little bit about the paint. It's a major part of the system. We talked about a little bit about how we would test these products to achieve the quality, the consistent quality that we want. And then certainly in the real world testing, we have to know what's going to happen in service. For further information, we put this together. Certainly the National Coil Coatings Association is a great reference to all things coil coating related, not just paint. Definitely check out our AkzoNobel Canopy app. It's full of great information, AkzoNobel specific products, product data. We can have hard copy print versions sent to you as well, should you like that. But at the end of the day, an educated customer makes the best decisions. And hopefully we did that for you today. Any questions?
How do you get the texture in the crinkle coating?
Yeah, so that's a good one. So that's actually a chemical reaction that's happening in the curing process, in the curing oven. So to cross-link, like I mentioned before, to make these chemical bonds, there's certain chemicals, there's catalysts and cross-linkers that have to have heat applied to make a chemical reaction. So that's what happens to make the normal coil-coated film. And then to make the crinkle coating, we add different cross-linkers and different catalysts that react at a different rate to the same amount of heat. So if you apply 500 degrees, the normal catalysts and cross-linkers will react as they normally would to make a smooth finish, but the additional catalysts and cross-linkers react quicker. So what they do is they actually make the film cross-link first, and they pucker up. So if you look at a crinkle under a microscope, these valleys, peaks and valleys, and every peak and valley meets at a point, and so it looks like a star, right? And these crinkle things are radiating from a center point of the star. That's where that reaction happened first that made it pucker up. So then when the rest of the coating is cured a second later, it sets all of that in place. So you have the waviness, the crinkling. It's not easy to achieve either. That's something to do on a coil line. It's not easy to do. Any other questions?
You said something about different colors, but were UV light into the primer?
Yep.
What colors are they?
So, all right. So if you look at there's a spectrum of visible light, and it's our rainbow, Roy G. Biv. It's our rainbow, and that spectrum of light goes from UV down to IR, and so the more blue, purpley colors, they allow UV light to transfer through more. When you see a color, what you're actually seeing is the light that wasn't reflected back at you. So your shirt, I'm seeing that color because that's actually the color that is being reflected back to me. All the other colors are being absorbed. So yeah, those blues, purples on that end of the spectrum, and then great hiding colors would be like blacks and reds, things like that.
When we have customers come back, don't happen very often, but every, in 5 or 10 years, they're having chalking and fading.
Yep.
What, generally speaking, what's happening with the paint system to fail in that regard?
Okay, so chalking and fading are two very different failures. The first would be chalking. So chalking is where the actual polymer resin is breaking down. Usually initiated by UV light. It doesn't have to be, but then moisture will do it too. But the UV light is very intense, okay? And it actually initiates chemical reactions. So resins that might not be as UV stable as others will over time begin to break down from this UV light, creating these reactions that are happening in this dried film. They can still happen. And those resin particles, they begin to split apart. And what it's doing is you have this really nice, smooth, continuous layer of a resin, and now these little areas are starting to fall apart, and they turn into chalk. The fading, that's completely different. That's where the actual color of the system, that is also being attacked by UV light and other things, moisture, where it initiates a completely separate sort of chemical reaction that begins to break those down. So like an organic pigment, which I mentioned before, not very thermally stable, not really stable in general overall, they tend to break down the quickest, right? And so as these organic pigments break down, the color goes away, and then you have that color change. As opposed to like our ceramic pigments that are highly durable, you see much less fade because they're rather inert. These chemical reactions don't happen to break them down through. So the fade is a change of a color, the pigments, generally, and then the chalk is the actual breakdown of the resin. It's just starting to flake off into a powder. The questions, those are good ones. Well, thank you, everyone. Enjoy the rest of the show.